Check it out now, y'all.
NanoHub U, online instruction.
Hi, welcome back. We're going to focus on this lecture on trying to explain the physical origin of Pauli's exclusion principle. The implications of Pauli's principle is not so obvious, so we're going to try to tie it into a variety of different topics here, try to provide an understanding of what actually is going on. So just to remind you what we're trying to explain, we're trying to explain why electron states populate the quantum energy levels in atoms this way and not this way, right? So why don't all these electrons condense into one ground state and fill up the lowest energy state? And the simple answer for that question is stated in Pauli's principle, which says that no two electrons in a quantum system can occupy the same quantum state or have the same quantum numbers. And so that means that rather than the electrons have to fill up these states accordingly, even though the energy levels of these states are considerably higher than it would be if all the electrons could condense down here. So what we're trying to do is we're trying to provide some physical insight into why this happens. Now, to provide that insight, I think it's better to discuss a specific problem and try to work through that specific problem than it is to discuss the issue in very general theoretical terms. So what I'm going to do is, in this lecture, I'm going to focus on the helium atom, right? And I'm going to try to explain the problems that arise when you try to calculate the energy levels for electrons in helium. So helium is the next simplest atom past hydrogen. Helium has 2 electrons or 2 protons in the nucleus. And it turns out those 2 electrons cause a significant problem when you try to solve Schrödinger's equation. And I like to try to explain that to you in a simple way. So to begin, let's review what we know about hydrogen, right? Hydrogen, there's 1 proton, there's 1 electron in the ground state orbit. The interaction potential energy is just our E squared over R term that we've seen for the past 2 weeks. Except in this discussion, what I'm trying to do is I'm trying to keep track of the charge on the nucleus. So I'm going to use the symbol capital Z to try to keep track of the charge on the nucleus. So for the hydrogen atom, Z is equal to +1 times the electronic charge, and it's a positive number. When we go to helium now, helium's got 2 electrons and 2 neutrons, or 2 electrons and 2 protons. So Z is equal to +2. And if we try to write the interaction potential energy term that's appropriate for this system, what we find that there's a electrostatic interaction between an electron in the nucleus, right? And 1 electron's position is designated by the parameter R1. The other electron position is designated by the parameter R2. So the second electron also interacts with the nucleus and gives rise to an interaction potential energy term like this. But now, in addition, there's a repulsive term because the 2 electrons will interact one with respect to the other, right? And these 2 electrons will repel each other because they've got the same polarity of charge. So we have to include a repulsive interaction term, which is written here in red, right? It's just the electronic charge. It doesn't involve the nucleus. And now the separation between the 2 electrons becomes important. So we have to symbolically include that separation, and we do that by just writing R1 minus R2. And that gives rise to an interaction potential energy that looks like this. And it's this term here, this repulsive term that causes all the problems. And I like to try to explain that to you in a simple way. So first question is, what are the energy levels of the electrons in a helium nucleus? Well, experimentally we can answer that question because we can take the helium atom and we can strip one electron from it, and we can find the minimum amount of energy that has to be added to the helium atom in order to remove one electron. That energy is referred to as the ionization energy, and for helium it turns out to be about 24.6 electron volts. So if you have a helium atom and you want to take one electron away from it, move that electron to infinity, you've got to supply this 24.6 eV worth of energy. The next, after you pull out one electron, then you've got one electron left. This one electron is bound to the two protons, right? And to remove this electron from these two protons requires considerably more energy because this electron is now strongly attracted to this +2 charge. And it turns out experimentally it takes about 54.4 electron volts to remove that second electron. So the total energy that has to be put into a helium atom to remove both electrons and move both electrons to infinity is just the sum of 54 plus 24.6. It's about 79 electron volts. You can do the arithmetic, okay? So it takes 79 electron volts to completely ionize the helium atom. So the question becomes, what does Schrödinger predict? Because Schrödinger predicts the energy levels for these various electrons. How closely does Schrödinger's model fit the experiment? So I try to work through that in this slide. And of course, the problem is that when you insert, well, first of all, you need a wave function, right? So you have to write a wave function down that describes both electron 1 and electron 2, and this is referred to as a two-particle wave function, and we're going to talk about that more in this lecture. But in addition, you have to write down the interaction potential energy that the electrons experience, and that interaction potential energy is going to contain three terms now. Two terms are going to just describe the attraction of the electron to the nucleus. The third term is going to describe the repulsion of the two electrons, one with respect to one another. When you include this repulsive interaction, you cannot solve Schrödinger's equation anymore, right? It's very difficult to find an analytical solution. So what do you do, right? What do you do? Well, you make an approximation. And the simplest approximation is to say, let's pretend there's no repulsive interaction between the two electrons. If there's no repulsive interaction between the two electrons, then this term goes to 0. The interaction potential energy then just becomes the sum of the two attractive terms in this total potential energy. And it turns out when you substitute this form for U back here into Schrödinger's equation, you can then separate Schrödinger's equation into two separate differential equations. One equation just describes electron 1. The other equation just describes electron 2. And so these two equations are referred to as single particle equations, right? They're single particle Schrödinger's equation, and they involve single particle wave functions because the wave function just as a function of the coordinates that describe electron 1, or the wave function is just a function of the coordinates that describe electron 2. So this separation follows naturally once this term here is neglected. The implications, right? The implications of that separation are that you can now calculate the energies of these two electron states. And to do that, you have to take into account the fact that the positive charge on a nucleus is now 2, right? And so you can use the results from Schrödinger's equation for the hydrogen atom. Turns out you just pick up an additional factor of z squared, where z is equal to 2 in this case. And what you find is that the total energy of those two electrons in this independent particle approximation is just minus 108.8 electron volts. right? So this minus 108.8 electron volts should be compared to the minus 79 electron volts that you get from experiment. And what you can see is that there's no comparison between the two. There's a substantial error. And that substantial error just indicates that this term is actually very important in solving Schrödinger's equation. Okay? So that's the argument that this term has to be included somehow, right? This term has to be included somehow. How do you include that term? Well, there's a large number of approximations that have been made over the years. The one I like to refer to is the one that it tries to mimic the second electron by a shielding of the second electron by the first electron. And that shielding argument just says that the total charge on a nucleus is reduced to some effective charge on a nucleus. And the effective charge on the nucleus is just the actual charge Z, which for helium is 2, minus some script S number. And this script S number has to be calculated somehow by some theory. And it turns out that for helium, there's been some very nice calculations done back in the 1930s that indicate that S is on the order of 5/16. And when you incorporate that shielding, right, when you incorporate that shielding into the Schrödinger's equation, then what you find is that you can predict the energy of the two electrons, the sum of the energy of the two electrons to be minus 77 eV. You compare that to minus 79 eV, which is measured experimentally, and you see the two results are much closer in agreement. Now, what that implies is, right, that implies that when the electrons orbit the helium nucleus, there's actually a correlation between their positions, right? It just basically means that this configuration here is favored over this configuration here, because this configuration, both electrons see the full potential energy of the nucleus. Over here, this middle electron serves to shield the outermost second electron, and that tends to reduce the total energy of the system and brings an experimental or a theoretical calculation into pretty close accord with experiment. So the problem is when you start to introduce additional electrons into the system, they start to interact with one another. You have to properly take that interaction into account. If you don't, you get the wrong answer. One way to take that interaction into account is to realize that there's some sort of a correlated motion between the two electron states. Now, what that implies is that you cannot write the wave function, right? You cannot write the wave function for two electrons in terms of the product of the wave function for one electron times the wave function for the second electron. So if there is no interaction between the electrons, this is a valid approximation, right? But as soon as there's an interaction that occurs between the two electrons, this approximation breaks down, and it's this breakdown that's the underlying reason why Pauli's exclusion principle is valid. So this is a hypothetical two-particle wave function. This hypothetical two-particle wave function involves quantum numbers for electron 1, and it also provides the position or the coordinate R1 for electron 1. It also provides the quantum number for electron 2 and the coordinate or position for electron 2. And the fact that you simply multiply these two things together, that's the approximation that starts to break down when there's a strong interaction between particles. And of course, that strong interaction occurs between electrons because they have the same charge polarity. So I'd like to try and illustrate this idea in a little bit more detail. And what we're, of course, trying to do is we're trying to write down a better approximation for a two-particle wave function that could describe the electrons in helium. And in the process of trying to write that wave function down, we're gonna gain some insight into why Pauli's exclusion principle is valid. And so I'd like to do a thought experiment. I'd like you to think about two cases. Case one is when I have two electrons, or let's say two particles, and these two particles are distinguishable. You can tell the difference between them. They might be identical, right? These two particles might be identical. They don't interact, but you can tell the difference between them. And that just simply means, what do I mean when I say you can tell the difference between them? That just simply means that the separation between R1 and R2, so if these are the wave functions that represent the two particles, right? If the separation between these two particles is greater than the de Broglie wavelength of those particles, then you can distinguish them. You can track them. And when you track them, then you can, for instance, color one red, you can color the other one blue, and you follow the motion of the blue particle or the motion of the red particle, because the wave functions that describe these two particles are completely distinguishable. You can tell them apart. That has important consequences. That very simple realization that you can distinguish the two particles has important consequences, and I try to illustrate that in this slide. And I'd just like you to consider a before and an after scenario. The before scenario is that I've got one particle colored blue. It's got energy level E1, which is in blue. It's got a position vector R1, which is in blue. And then there's a second distinguishable particle with energy E2 with position R2, and we color this second particle red. Because the two particles are distinguishable, I can write the two particle wave function as the product of the wave function for particle 1 times the wave function for particle 2, as I've written here. And what we want to do is now we want to exchange the two particles. So we want to imagine that particle 2 goes to position R1, and particle 1 goes to position R2, right? And that just simply means that this two particle wave function, which is the product of the single particle wave functions, has to be altered as I've drawn here. So R2, the position R2 now assumes the quantum numbers N1, and the particle at position R1, right, now assumes the quantum numbers that are appropriate for particle 2. Because the particles are distinguishable, you can tell the difference between this configuration and this configuration, right? The red is switched, the blue is switched. And you can also tell the difference from the wave function, right? So these wave functions are distinguishable one from another, and they accurately reflect the fact that the particles have been exchanged, one with respect to the other. So that's the case of the distinguishable particles. But unfortunately, when you start to deal with electrons and atoms, these electrons become indistinguishable one from another. Every electron looks the same as every other electron, and that just simply means that we can't distinguish two electrons in space, and so we can't color one electron red, we cannot color the other electron blue, and furthermore, the separation between the two electrons is so close that they get intermixed. There's no way we can follow, let's say, the motion of the first electron with respect to the second electron, because everything is intermixed, one with respect to the other. So this is referred to as the case of indistinguishable particles. And what happens is, if I go through a simple thought experiment like I did before, I now have two particles. These are now two electrons. One electron has quantum numbers n labeled by the blue values. They have an energy E1. They're at some position R1. The second electron has quantum numbers N2. It's got an energy E2, and it's a position R2. But I can't I can't tell the difference between them, so I can't color the particles red and blue. I can, though, imagine switching the location of particle 2 with particle 1. So I can take the electron at position R2 and I can move him to position R1. I can take the electron at R1. I can move him to position R2. And then I have to modify the wave function, which I approximate as the product of these two single particle wave functions. So when I do this switch, right, the wave functions are distinguishable. I can tell the difference between this wave function and this wave function, right? But I cannot physically tell the difference when I look at the two electrons. And the reason I can't is because I can't color the electrons. I don't have a color form. So physically, the real situation is indistinguishable, right? I switch the two particles and I can't tell the difference. But if I approximate the two particle wave function by the product of these two individual wave functions, I can clearly see there's a difference. So there's an incompatibility here, right? There's a fundamental inconsistency between the mathematics and the physical situation. And this inconsistency forces me to conclude that I can't use this form of the wave function when the particles all look the same. And that, of course, is the case for electrons and atoms. You might recall from homework number 2, I asked you to calculate the de Broglie wavelength of electrons as a function of their kinetic energy. And if you did that homework exercise, you remember you got a plot that looks something like this. And the point I just want to make is that the typical energies for electrons and atoms that we're discussing, those typical energies lie out here in the range between 10 and 100 electron volts, right? That means that the de Broglie wavelength of an electron is on the order of 0.5 to 1 nanometer. But when you confine the electrons to atoms, right, they typically have radii of orbits that are given by this Bohr radius A0. So the de Broglie wavelength of these electrons tends to be on the order of 100 times bigger than the Bohr radius of an electron in a hydrogen atom. And that just reinforces, I think, I hope it reinforces this picture, right? So these de Broglie wavelengths are large compared to the separation between the electrons. That's another reason why these two electrons can no longer be distinguished when you, for instance, confine them to a helium atom. Okay, so how do you solve this problem, right? How do you solve this problem? And one way to think about it is to say that, okay, I don't know the exact form. I don't know the exact mathematical form for this appropriate two-particle wave function, but I would like to believe that if I take psi star psi of this two-particle wave function and then flip the two particles and take psi star psi again, I would like to believe that the probabilities that I get for those two situations where I just interchange two identical particles, I like to believe that those two probabilities are identical, right? So there should be no change in the probability that I find the electron at some position if I switch the electron with its neighbor. And that implies, right, this simple fact implies that this type of an equation has to be true. And the only way that this type of an equation can be true is if these two particle wave functions are equal after you interchange particles, or they change sign, they change polarity if you interchange particles, right? So this very general restriction is the fundamental result of this lecture, that if you're gonna write a two-particle wave function down for identical particles, indistinguishable particles, they have to obey either of these two conditions when the particles are interchanged, one with respect to another. So I end the lecture with a summary that you can read on your own. It sort of summarizes what I tried to say and what I tried to work through in the discussion of this lecture. And what I'll say is, when you come back, we're going to talk a lot more about what the form of these two wave functions mean in terms of proper forms for wave functions for two electrons in atoms. So we'll take this very general discussion and we'll start to apply it to specific cases, and we'll find out that electron wave functions have to satisfy this condition here, right, for them to be valid. And this condition here is essentially equivalent to the Pauli exclusion principle. So that's going to be the topic of the next lecture. So hope to see you for that. That'll be available. That'll be fourth lecture this week. So thanks a lot.